Quartz sensors are the best choice for smart cables. Quartz sensors easily meet the smart cable requirements. The full-range absolute sensors will not clip, and the inherently digital signals have parts per billion resolution. They are compact, deployable in any orientation, and provide direct monitoring of cable health. Hundreds of thousands of pressure and acceleration sensors have been deployed with millions of sensor years of reliable operation. The sensors must make short-term high-resolution measurements of earthquakes and tsunamis and have excellent long-term stability to measure geodesy and sea level changes. The seismic plus oceanic sensors, called SOS, contain two absolute pressure gauges, one triaxial accelerometer, one digiquartz barometer for A0A, and nano-resolution processing electronics. Temperature compensated and linearized RS-232 outputs are provided from all sensors. This is a plot of the resonator noise floor that shows parts per billion resolution. The NOAA DART system was developed in the 1990s. In November of 2004, we presented a joint paper at the Oceans Conference in Kobe urging an expansion of the existing 6 DART systems. There was little interest until 240,000 people were killed in the Sumatra tsunami only 1 month later. The first micro-tsunami across the Pacific was measured in 2010. The Tohoku tsunami was measured with quartz step sensors in real time with the donut cable system. 10 hours later, the tsunami was measured offshore Monterey, California. Dr. Hino and his colleagues had deployed remote bottom pressure recorders near the epicenter. On March 9th, a magnitude 7.3 precursor event caused a drop of about 10 centimeters that was followed by another 1.5 centimeters over the next 2 days, prior to the big disaster on March 11th. A smart cable system could have delivered these critical measurements in real time. The SNET disaster warning system uses 2 quartz depth sensors and 3 quartz accelerometers. The quartz triaxial accelerometer and the RBR probe compared well to a nearby broadband seismometer. The quartz accelerometer has a plus or minus 3G range and is orientation independent, unlike the broadbands that need to be leveled and clip under even moderate earthquakes. Because of the internal alignment matrix, tilt measurements can be made in any orientation. The University of Washington deployed their smart cable system with the SOS module off Monterey, California in 2017. They made nano-resolution measurements for 30 months. An earthquake in Mexico was measured on all axes with the triaxial accelerometer and on the vertical axis with the pressure sensors. The SOS also measured the tiny signals from an underground nuclear test by North Korea 9,000 kilometers away. The acceleration signals were micro-Gs and the pressure signals were microns. The in-situ A0A calibration method corrected the drift to 1 millimeter per year. Comparisons of drift-corrected A0A measurements to satellite altimetry were excellent. High-fidelity long-term measurements of platform tilt were made with the plus or minus 3G triaxial accelerometer. The accelerometer is a good measure of cable health and external disturbances. This is the model noise floor for the quartz triaxial accelerometers and tilt meters overlaid onto the desired smart cable specs. The QA15 triaxial accelerometer meets all the requirements and can be deployed in any orientation without leveling. Vault tests by the University of Washington showed smaller tidal residuals on the QA15 accelerometers than on the broadband.
The platform and the floor of the vault tilted by many microradians over several months. However, the agreement between the two triaxial accelerometers and the two tiltmeters was good to a fraction of a microradian.
Spar Webb of Columbia University measured the velocity spectra of the QA15 triaxial accelerometer that was deployed for a year offshore New Zealand. Spar points out that the QA15 has a similar noise floor to the Cascadia broadband OBSs at almost all frequencies. Most importantly, the QA15 does not need to be leveled and is expected to never clip, whereas the OBSs would clip on about a 4.7 regional event.
There have been hundreds of deployments of SOS modules worldwide. The latest, most advanced smart cable design will be deployed in Cascadia by the University of Washington.